Today we are going to first look at radiant heat exchange between two finite sized black surfaces. Last time you will recall that when we stopped, we had derived the expression for heat exchange, rate of heat exchange between two differential areas dA1 and dA2 at temperatures T1 and T2. And the expression which we had derived was the following. Let me first repeat that. The expression which we had derived last time for heat exchange between two differential areas dA1 and dA2 was dQ 1 to 2 is equal to sigma by pi cosine beta 1 cosine beta 2 divided by L squared multiplied by T1 to the power of 4 minus T2 to the power of 4 dA2 dA1. That was the expression which we had derived. Now, that is where we stopped, we got this expression. Now, we want to extend this expression to the situation where we have two finite size black surfaces maintained at uniform temperatures T1 and T2. All right, that is what we want to do. So, let us go back, see the sketch again. These are the two surfaces. This is surface A with an area A1. This is the surface with the area A2. Let me write this again in big letters. It is rather small here. This is A1. This is the finite area A2. They are both black, and A1 is maintained at a temperature T1. A2 is maintained at temperature T2. We would like to know what is the net radiant heat exchange rate between A1 and A2. Now, suppose I take some differential area dA1 on A1 and I take some other differential area dA2 on A2, join the two areas by this line and let the length be L like last time, then we know the expression for heat exchange between dA1 and dA2. All right. So, let us extend that now. Obviously, if we want to know what is the value for two finite size surfaces and we know the expression for two differential areas, it follows that all we have to do is to integrate the expression which we have for differential areas. And we will have to integrate over the area A1 and we will have to integrate also over the area A2, which means the expression which I have put down here for dQ1 to 2. If I want Q1 to 2, let me cancel out the d on this side. If I want Q1 to 2, that is the heat exchanged by radiation between A1 and A2, I will integrate this expression twice over the area A1 and A2. All right, that is what we will do, and that is our expression for Q1 to 2. Now, T1 minus T1 is a constant, T2 is a constant. So, T1 to the power of 4 minus T2 to the power of 4 is a constant. I can take it outside the integral. Let me also take sigma outside the integral. All right. So, if I take both these outside the integral, which is permissible, then I will end up with the expression. If I do that, then I will end up with the expression, and let me show that. I will get, as is written here, if the surfaces A1 and A2 are at uniform temperatures T1 and T2, then net radiative heat exchange rate between A1 and A2 Q1 to 2 becomes the following. I have just taken sigma and T1 to the power of 4 minus T2 to the power of 4 outside the integrals, because they are constants, and the quantity within square bracket is the integral which I will have to perform first over the area A2 or and then over A1 or vice versa, it does not matter. Now, let us again, like in the earlier situation, define a shape factor. This expression is fine, but let us define now and put it in terms of a shape factor. So, we will say defining a shape factor, defining the shape factor of surface 1 with respect to surface 2. Let me repeat that, defining the shape factor of surface 1 with respect to surface 2, f 1 to 2, defining it as 1 upon a 1, the quantity which I had earlier within square bracket, all that integral a 1 integral over a 2 cosine beta 1 cosine beta 2 upon pi l square dA 2 dA 1. If we use this definition of shape factor, our expression for q 1 to 2 becomes q 1 to 2 is equal to f 1 to 2 sigma t 1 to the power of 4 minus t 2 to the power of 4 into a 1 multiplied by a 1. Now, notice again how we have defined f 1 to 2. f 1 to 2 is defined, f 1 to 2 is the shape factor of 1 with respect to 2, surface 1 with respect to 2, and we have defined it in such a manner that it represents the fraction of the radiation emitted from 1 which is intercepted by 2. Note that the definition is not just some arbitrary definition, we have defined it in that manner. So, that if I take the first part of this f 1 to 2 sigma t 1 to the power of 4 into a 1, you can see sigma t 1 to the power of 4 into a 1 represents the total amount per unit time emitted from the surface 1. If I multiply by f 1 to 2, I get the amount that goes from 1 towards 2 is intercepted by 2, and because 2 is black is also absorbed by 2. Okay. So, again I am defining shape factor with that physical meaning in mind. It is not some arbitrary definition with an integral in it, keep that in mind. All right. So, we could also define a reverse shape factor. I could define a shape factor in the reverse direction, that is from surface 2 to surface 1. I could say f 2 to 1 in exactly in the same fashion. In a reverse direction I could say f 2 to 1, f 2 to 1 is the shape factor of 2 with respect to 1 is equal to 1 upon a 2, the integral over a 1, the integral over a 2 cosine beta 1 cosine beta 2 pi l square dA 2 dA 1, the same quantity within the square bracket that we had earlier. And we have therefore, we could say q 1 to 2 is equal to f 2 to 1 sigma t 1 to the power of 4 minus t 2 to the power of 4 multiplied by a 2. And we should note again, like we did earlier, that the two shape factors f 1 to 2 and f 2 to 1 are related by a reciprocal relation. F 1 to 2 a 1 is equal to f 2 to 1 a 2. All right, keep this in mind, that is a reciprocal relation relating the two shape factors. They are not two independent quantities. So, we have expressed the quantity q 1 to 2, we have expressed the quantity q 1 to 2, which represents the net radiative heat exchange rate between 1 and 2 in three ways. First, we have expressed it without a shape factor, that was the first expression which we got simply by putting two integrals on the expression for dq 1 to 2. Secondly, we have expressed it in terms of f 1 to 2 and said q 1 2 is equal to f 1 to 2 sigma t 1 to the power of 4 minus t 2 to the power of 4 multiplied by a 1. We have expressed it also in the reverse manner by saying q 1 to 2 is equal to f 2 to 1 sigma t 1 to the power of 4 minus t 2 to the power of 4 into a 2. We got three different ways, all equivalent ways of for the same quantity. All right. Now, we want to move ahead. So, we have considered two situations. What are they? We have considered heat exchange rate between two differential areas dA 1 and dA 2. We have considered heat exchange rate between two finite sized areas A 1 and A 2. Now, we say all right, suppose we have a situation in between the two, that means we want to consider heat exchange by radiation between a finite black surface, that is one area is big and one is small. Small means like a differential area, a small black surface A 1 which is like dA 1. Suppose we have this situation, a small area and a large area, all right, and we want to calculate heat exchange rate between them, heat exchange by radiation between them if they are maintained at two temperatures T 1 and T 2. So, that is the next situation, the third situation, which is in between the first two situations that we have considered. And this is rather easy to derive, it should not be a problem. Let us go back again. So, let me again repeat, we are deriving the heat exchange by radiation between a finite black surface A 2 and a small black surface A 1, that is what we are doing now. A 1 can be treated like dA 1, keep that in mind, because it is small. So, to derive it, go back to our initial expression for dq 1 to 2. Okay. What was our expression? dq 1 2 between two differential areas, sigma by pi cosine beta 1 cosine beta 2 dA 1 dA 2 divided by L squared multiplied by T 1 to the power of 4 minus T 2 to the power of 4. That is our expression for heat exchange by radiation between two differential areas. Now, I mean we want to modify this expression when one area is small and one is large. The small area is A 1 and we can treat it like dA 1. That means, I can simply replace dA 1 by A 1, because it is like it is a small area, all right. Once again, T 1 is a constant, T 2 is a constant. So, I can take this expression outside the integral sign. So, what do we get now? If A 1 is small, if A 1 is small, I need not perform the integration over A 1 and treat dA 1 as just A 1, and I will simply get q 1 to 2 in this case is equal to, the quantity within square bracket will be integral over A 2, I have to perform only an integral over A 2 cosine beta 1 cosine beta 2 divided by pi L squared dA 2, the whole thing multiplied by sigma A 1 T 1 to the power of 4 minus T 2 to the power of 4. That is what we will get as the expression for q 1 2. So, all we have done is substituted A 1 for dA 1, because A 1 is small, equivalent to a differential area, taken T 1 to the power of 4 minus T 2 to the power of 4 outside, because it is a uniform, they are at uniform temperatures and therefore, that expression is a constant, and the rest we have put within the square bracket, obviously is a shape factor. So, I can say this is equal to f 1 to 2 sigma A 1 T 1 to the power of 4 minus T 2 to the power of 4, all right. So, again now I have an expression for the heat exchange by radiation between a small surface A 1 and a large surface A 2, and the expression is given here. I can use the first expression which I am showing just now, or I can use the second expression which is in terms of a shape factor f 1 to 2 being nothing but the quantity within the square bracket. So, the shape factor f 1 to 2 is nothing but the quantity within the square bracket. All right. And again it has the same physical meaning, it stands for the fraction of the radiation emitted by 1 which goes towards 2 is intercepted and is intercepted by 2. That is the meaning of the shape factor. So, we have got three expressions for the heat exchange, net heat exchange rate between surfaces, between black surfaces. The surfaces may be differential, that means they may be very small surfaces dA 1 and dA 2, small relative to the distance between them, that is what we mean when we say small. Or there may be two finite size surfaces A 1 and A 2, may be flat, may be curved, we have put no restrictions on them, but at uniform temperatures T 1 and T 2, and The third situation is one of the surfaces may be small, one may be large, and we have for each of these we have expressions for q 1 to 2, or in the first situation dq 1 to 2, because they are differential areas. Now, in all these expressions that we have derived, notice the importance of the quantity which we have defined as shape factor. See, it keeps recurring all the time, and it will therefore be useful for us to spend a little time talking about the shape factor and certain relations between shape factors. So, we will spend a little time now talking about that before we move on to doing more heat exchange calculations by radiation. We have done some calculations, we have got expressions for 3 situations of heat exchange by radiation between black surfaces, but I want to spend a little time talking about shape factor, how to calculate it, relations between shape factors, before we again move ahead to doing calculations for heat exchange by radiation for other situations. Now, let me again define shape factor. I have done it earlier, but I repeat. The shape factor, it is written here, the shape factor of one surface with respect to another is the fraction of the radiation leaving the surface which is intercepted by the other. Okay, that is our definition of shape factor. By definition, shape factor must be between 0 and 1, a number between 0 and 1. So, let me write that here. By definition, shape factor f, whatever it be between two surfaces A and B, must be between 0 and 1. Well, it is bounded always by definition. Now, let us make some remarks on shape factors. The first remark which I have made earlier and I am repeating is that between the shape factors of two surfaces 1 and 2, the shape factor of 1 with respect to 2 is called f 1 to 2, the shape factor of 2 with respect to 1 is called f 2 to 1. Between these two shape factors, by definition, we have the relationship f 1 to 2 a 1 is equal to f 2 to 1 a 2. All right, we have this definition. By definition, we have this relation. This is called the reciprocal relation. Now, it is an obvious relation because it follows from the definition, but the real reason why I am mentioning it is that to point out the utility of this reciprocal relation. The relationship, the reciprocal relationship is particularly useful when one of the shape factors, either f 1 to 2 or f 2 to 1 is unity, then it is particularly useful. All right. Now, when does this happen? When is the shape factor f 1 to 2 or f 2 to 1 equal to unity? When if you ask the question, you say obviously if all the radiation emitted by 1, by the surface 1 is intercepted by 2, none of it goes back to 1, mind you, then the shape factor of 1 with respect to 2 is 1, unity, or the reverse, f 2 to 1 will be unity when all the radiation emitted by 2 is intercepted by 1, it goes nowhere else, it does not even go to 2. All right. And when does this happen? This will happen when the surface 2, I am talking now of f 1 to 2, f 1 to 2 will be unity when the surface 2 completely surrounds 1 and the surface 1 is completely convex. Let me give an example. Suppose I have a sphere. All right, this is a sphere, and let us say sphere or a spherical shell, it does not matter, and it is at a, I call it surface 1. And let us say this sphere is inside this room, it is a sphere of any size inside this room. So, let me draw this room here, it is a rectangular room So, let us say this is the room, it is a rectangular room with 6 faces. On this paper I am drawing only 4, but remember it has 6 faces. So, I will call this as the surface 2, the room, all right. Now, consider radiation emitted from the surface of 1. Surface 1 is spherical, it is a sphere. Radiation emitted from any element on surface 1, anywhere. All right, consider that radiation emitted from the surface anywhere on surface 1 has to first hit 2, it has no choice. Therefore, in this case f 1 to 2 is equal to 1, got it. But mind you, suppose just to illustrate to you, 2 surrounds 1, but that is not enough. No radiation from 1 should go back to 1 itself. Consider for instance that the object inside, that is 1, is not a sphere, but a shape something like this. Let us say this is 2, this is the surface 2 still, all right, which is this room. But consider that surface 1, instead of being convex as a spherical shape is, suppose it had some shape like this, instead of being a sphere which is inside, let us say it has some shape like this, all right. Now, let us say this is surface 2. Now, you can see if I take an element on this surface, radiation going out from this element, any element like this, some of it will go and hit the surface 1 itself, all right. So, if the surface of 1 is concave in some place, not everywhere, but any place, then part of the radiation from 1 will come back to 1 itself, in which case f 1 to 2 will not be equal to 1, all right. So, the two conditions for f 1 to 2 to be 1 are 2 should completely surround 1, so that all the radiation from 1 can go towards 2 and no other surface. Secondly, 1 itself should not have a concavity in it, so that radiation from some part of 1 goes to 1 itself. It must all go towards 2. Now, these are situations. So, the first one is a situation in which f 1 to 2 is 1. Now, in such a case, if I ask you what is f 2 to 1, you will straight away say, for this case f 2 to 1 is equal to a 1 by a 2 multiplied by 1, that is a 1 by a 2. I do not have to use the double integral for f 2 to 1. If you see from the definition, f 2 to 1 will have a double integral equation, which is not a double integral expression, which is not easy to solve. But using the reciprocal relation, I can straight away tell what is f 2 to 1 and say simply f 2 to 1 is equal to a 1 upon a 2. So, you see the benefits of using the reciprocal relation in some cases. So, that is the first remark that we want to make about shape factor. The second remark which I want to make about shape factor and which is rather important is the following. Let me just show that. The second remark which I want to make is the shape factor, the value of the shape factor depends only on the geometry and orientation of the two surfaces. You will notice when we put the definition, we took temperature outside the definition. There is no T1 or T2 in that definition. So, shape factor does not depend on the temperatures of the surfaces, it depends strictly on the geometry. What are the shapes, what are the sizes of the surfaces involved, what are the relative orientations, how are they oriented with respect to each other. That is what shape factor depends on. Okay. So, because of this definition, I can do shape factor calculations in advance for a variety of shapes and situations encountered in practice. I do not need to know their temperatures for calculating radiant heat exchange. If there are geometries encountered in practice, frequently encountered in practice, for those geometries, for those shapes, sizes, orientations of surfaces, I can do shape factor calculations and have those available in the form of values, which I can use any time for doing radiant heat exchange calculations, and that is what people do. For a variety of situations, for a variety of common situations which occur in practice, we have with us shape factors calculated by other people, and we use those for doing our calculation. We do not sit down and try to evaluate double integrals most of the time. So, I will say values of shape factors are available for many common configurations. Now, this figure, it is a little small, so let me explain it, is a figure which shows the shape factor between two parallel rectangles of equal size. The shape factor between two parallel rectangles of equal size. Since it is not so clear, let me draw it again. One parallel rectangle could be this, all right, and the other parallel rectangle of equal size, which is below, is this, all right. I call this the surface 1, A1, and this 2, A2. A1 and A2 are two rectangles of equal size, parallel to each other and opposite each other, like the floor and the ceiling of this room. These are two parallel rectangles of equal size facing each other, or the two walls of this room, the two side walls which I am pointing to. These two are two rectangles of equal size facing each other, or the other two walls, one behind me and one in front of me, they are also like that. You understand? So, any two walls, the floor and the ceiling, are two rectangles, two parallel rectangles of equal size facing each other. The shape factor for that has been calculated, and that is what is given in this graph which is given here. The shape factor f1 to 2 here, f1 to 2 is plotted, is the value from the read off from the y axis, and it is given as a function of f1 to 2 is a function of two parameters L1 by d and L2 by d. That is how it is given. Okay. L1 and L2 are the sides of the rectangles. This is L1 and this is L2 are the sides of the rectangles, and d is the distance between the two rectangles. D is the distance between the two rectangles. Got it? So, the shape factor f1 to 2 is given as a function of L1 by d and L2 by d. That is what we have in this graph. So, anytime you have this situation in practice, all you have to do is, for the given situation, calculate the two parameters L1 by d, L2 by d, go to this graph. L2 by d is given on the x axis, this is L2 by d, and L1 by d is the parameter which is varying between each graph which is drawn here. This is the parameter L1 by d. So, in this case, this is the graph for L1 by d equal to 1, L1 by d equal to 2, L1 by d equal to 3. The final one which is dotted is L1 by d equal to infinity. So, all values of L1 by d from 0.1 to infinity are covered in this graph. Similarly, L2 by d is covered from 0.1 to 20. So, all situations in practice covered in this graph. So, for a given situation in practice, calculate L1 by d, calculate L2 by d, go to this graph L2 by d, go to the appropriate curve for L1 by d, read off the value of f1 to 2. That is what we will be, you will have to do. Okay. Now, this is just one, as an example I showed this. This is one example of shape factor calculations which have been done by somebody else, which are available to us in for usage whenever we have to do radiant heat exchange calculations. And such graphs or equations corresponding to these graphs are available for a very wide variety of common configurations, a very large number they are available. Let me show you one more example, so that you get the idea. Here is one more example now. Here is a shape factor between rectangles which are perpendicular to each other and have a common edge, something like this. It is drawn in small here, it is rather small here. So, let me draw it again. These are two rectangles like this is one rectangle, this is another rectangle, all right. This is, they have a common edge and they are perpendicular to each other, and the dimensions are L1 and L2 and W. So, one of the rectangles is L1 into W, the other one is L2 into W, and they are at right angles to each other. We would like to know the shape factor. Now, for this case also shape factor has been calculated, it is available to us, and what we have is on the y axis here we have f1 to 2, on the x axis here we have L2 by W, and the different graphs which are drawn here are for varying values of L1 by W. So, given a particular situation now, say this could be the floor of this room and one of the side walls, or the ceiling of this room and one of the side walls. There are two situations of two rectangles, right angles to each other with a common edge. Okay? Could be any one of these. Now, given this situation, calculate, if you have to do a radiant heat exchange calculation, calculate L2 by W, calculate L1 by W, and then from this graph read off the value of f1 to 2. So, f1 to 2 is a function of L1 by W and L2 by W. Got it? So, again this is a very common configuration, and somebody has done this integral for us and we have got the expression for us to use any time we need it. And like this, as I said, there are literally hundreds of situations for which shape factor calculations have been done, and the values are available either in the form of graphs, equations, tables, whatever it is, they are available to us to use any time we have to do radiant heat exchange calculations. So, this is the second remark. The value of shape factor depends only on geometry. It has been calculated for a wide variety of situations and configurations which are commonly used in practice, and these are available in textbooks, handbooks for us to readily use. The third remark which I want to make is the following, which I have made earlier and I am repeating. I am saying a surface has a shape factor with respect to itself if it is concave. This is a remark which I made a little earlier, but let me repeat it. What I mean is the following. Suppose I have a surface like this, a concave surface like this, surface 1. This is my surface 1, all right. It is concave like this, emitting radiation. It is obvious now, if I take some element on this surface, all right, then some of the radiation which is emitted, radiation is emitted in all directions of a hemisphere, but some of the radiation emitted is obviously going to come back to the surface itself. Okay. So, this is a case because of the surface being concave, it follows that f 1 to 1 is not equal to 0. On the other hand, if the surface 1 is say flat, suppose this is the surface 1, all right. And now, if I consider radiation emitted from any elementary area on this surface, you will agree with me that radiation emitted from surface 1 anywhere on surface 1 will go out like this and will not be intercepted by 1, right. So, this is a case where f 1 to 1 will be equal to 0, or let us take the case when surface 1 is let us say convex like this, okay. Then also f 1 to 1 quite obviously is equal to 0. Now, mind you, just to clarify, the surface 1 may be flat, the surface 1 may be curved, the surface 1 may be consisting of two flat surfaces together, that also may be surface 1. For instance, let us go back to this room. Here is our room. Okay. Let me draw it in 2 dimensions. This is my room, which I am sitting. If I want to do a radiant heat exchange calculation and I want to treat all the surfaces, the 6 surfaces of this room as being independent, then I will call them as 1, 2, 3, 4 and the 2 surfaces which I can't show here, which in 3 dimensions will be seen like this, all right, as 5 and 6. So, I will have 6 surfaces, right. Now, if I treat the 6 surfaces as surfaces independent of each other, f1 to 1, f2 to 2, f3 to 3, all for each of these surfaces will be 0. But let us say surface 1 and 2 are at the same temperature. So, for purposes of calculation radiant heat exchange, I can treat 1 and 2 as one surface, all right. Then it follows that 1 and 2 now, surface 1 and 2, if I treat it as one surface, call it as say surface A, all right. It follows that for this surface A, which consists of 1 plus 2 together, 2 rectangles together with a common edge, it follows for this case that the shape factor of surface A with respect to itself will be non-zero. So, for this case now, let me write it here. For this case, f 1 to 1 was 0, if 1 is only a flat surface, f 2 to 2 will be 0, but if 1 and 2, the 2 flat surfaces are treated as one surface together and I call it as A, that is 1 plus 2 I call as equivalent to a surface A, all right, some surface A, then f A to A is non-zero. Okay. So, a surface may be flat, a surface may be curved, a surface may be a combination of 2 flat surfaces, 2 curved surfaces, 1 flat surface and a curved surface, whatever it is, it is up to me to decide depending upon the radiant heat exchange calculation that I have to do. And for that situation, once I have defined what are my surfaces, then I have to see whether f1 to 1 or f A to A is 0 or non-zero. This is a remark about a surface having a shape factor with respect to itself. Now, let us go to one more relation which is important, and that is the following. Suppose I have an enclosure made up of n surfaces. Let us say I have some enclosure, and just to make things show that they are messy, I have drawn one as a flat surface, surface 1, surface 2 I have drawn as a convex surface, surface 3 I have drawn as a concave surface, then surface 4 again I have drawn as a convex and again as a convex surface. I have drawn a 5 surface enclosure in 2 dimensions here. Let us say these 5 surfaces make up an enclosure. I could think in general terms of an n surface enclosure making up an enclosure. So, the n surfaces may be flat, they may be curved, the curved surfaces may be convex or concave, it does not matter what. Now, if these n surfaces 1, 2, 3 up to n surfaces, if they make up an enclosure, then it follows that all the radiation emitted from any one surface, say surface 1, has to go to all the other surfaces, that is surface 2, 3, 4 etc. up to n, and to the surface 1 itself if f 1 to 1 is non-zero. So, I can state that as follows. I can say for an n surface enclosure, let me write that now, let me show that. For an n surface enclosure, f 1 to 1 plus f 1 to 2 plus f 1 to 3 plus dot 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 f 1 to n is equal to 1, because all the radiation emitted from 1 has to go to either to 1 or to 2, 3 up to n, all that must add up to 1. And if 1 is a flat surface or if 1 is convex, then this f 1 to 1 will be automatically we will put as 0. You follow? Similarly, consider the radiation emitted from surface 2. It follows that F2 to 1 plus F2 to 2 plus F2 to 3 plus F2 to n is equal to 1, and so on. If I consider the nth surface of this enclosure, Fn to 1 plus Fn to 2 plus Fn to 3 dot 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 Fn to n is equal to 1. You follow? So, I can write down n such equations for the n surfaces making up this enclosure. So, these are relations between all the shape factors when surfaces make up an enclosure, and we will use these. We can use these to calculate one shape factor from another. That is the advantage. The last remark which I want to make is the following. Suppose I have two surfaces 1 and 2. Let us say I have a surface 1, some arbitrary surface, may be curved or may not be curved. Let us say I have a surface 1 like this, and let us say I have some surface 2 like this, arbitrarily located in space, two finite size surfaces. And let us say I break up the surface 2 into two parts like this. I have broken it up into two parts. I call this as surface 3, this is surface 4. That means A2 is equal to A3 plus A4. The two surfaces 3 and 4 make up the surface 2. Now, radiation going from 1 towards 2, the fraction of radiation going from 1 towards 2 is F1 to 2. It follows that since 3 and 4 make up 2, that F1 to 2 must be equal to F1 to 3 plus F1 to 4. It follows, is not it? So, let me show that in writing. It follows that F1 to 2 must be equal to F1 to 3 plus F1 to 4 if the two areas A3 and A4 make up the area A2. Keep that in mind. But note, the reverse is not true. Many people sometimes will say F2 to 1, F3 to 1 and F4 to 1. These are the reverse shape factors in the reverse direction. This F2 to 1 is not equal to F3 to 1 plus F4 to 1. Keep that in mind. All right. This, from the definition itself you can see that this is not true. F2 to 1 is not equal to F3 to 1 plus F4 to 1. Please do not make this mistake. The additive relation which we can use is F1 to 2 is equal to F1 to 3 plus F1 to 4, and this follows from the physical meaning of shape factor. Radiation going from 1 intercepted by 2. If 2 consists of 3 and 4, radiation going from 1 towards 3 and from 1 towards 4, the sum of the two fractions must be equal to the first fraction F1 to 2. So, keep this in mind. The first relation is valid, the second is not. The first one is called the additive relation. So, these are various relations between shape factors that we have given, and the advantage will be obvious from various situations which we have to consider. Now, we will do some problems in which we calculate shape factors for a variety of situations, all right, so that you get used to using these relations. I am going to do some problems. So, the first problem I am going to do is the following. Let us do the following problem. Calculate the shape factor F1 to 2 between a small area A1 and a parallel circular disc A2. Here is the small area A1. Let me just shade it in red. It is a small area, differential area A1, and parallel to it a circular disc A2 is like this. So, we have let us say this table. On this table I have a circular disc. At the center of the disc, let me draw a perpendicular at the center of this disc and go up a certain distance h. At that distance h, consider a small area A1 which is like a differential area parallel to the plane of this table. All right, that is what we are talking about. we would like to calculate f1 to 2. We are going to use obviously the formula which we derived for shape factor between a small area A1 and a large area A2. We are going to use that formula. So, what is the formula? Let me just put that down. For such a situation, we know f1 to 2 for the case, this case with a small area, f1 to 2, if you go back in your notes, you will see is nothing but the integral over A2 cosine beta 1 cosine beta 2 divided by pi L squared dA 2. Okay, that is our expression. Now, let me go back to the sketch here. We must take our dA 2. In this case, we have symmetry. We want the radiation coming from one which falls within this cone. All right. So, since we have symmetry, for dA 2, I can take a ring of thickness dr at some radius r. We have got symmetry all over. I do not have to take dA 2 as r d theta dr in cylindrical in polar coordinates. I can take a ring of radius at a radius r of thickness dr. So, my dA 2 will be 2 pi r dr. Okay. Let us take that as our dA 2. So, take dA 2 to be, let me write that down, take dA 2 because of symmetry, we will take dA 2 to be 2 pi r dr. And therefore, I can now perform the integration. I say the distance between the two surfaces is h and the semi vertex angle, let me again show the sketch. I will say that the distance between the two surfaces is h, the semi vertex angle subtended by this disc, circular disc at A1 is alpha. Now, using our nomenclature, if I join A1 to dA 2, the distance between the two will be the capital L, which we have in our formula. This will be capital L, and the angle made by this line joining A1 to dA 2 and the normal, the two normals will be parallel to each other because the two surfaces are parallel to each other, and the angles, this will be beta 1 here and this will be beta 2 here, and they will be equal in this case. So, let us substitute into our expression now. We will get f1 to 2, we are going to express everything in terms of the angle as the variable beta 1. So, we will get f1 to 2 is equal to cosine beta 1, the second beta 2 is equal to beta 1. So, I can write it also as cosine beta 1 divided by pi. Now, instead of L, I will write L as h, the distance between the two surfaces, divided by cosine of beta 1 the whole squared, because beta 1 is my variable, and then for dA 2 I will write 2 pi, for r I will write h tangent beta 1, that is r, and for dr I get by differentiating h tangent beta 1, I will get h secant squared beta 1 d beta 1. All right, that is my expression, and I will have to integrate this from 0 till the semi vertex angle, which is alpha. So, I will integrate this from 0 to alpha, that is over the whole area, then I will cover the whole area of the disc. If I do that, now I am skipping the details here, you can do the simplification, you can see that the cosine beta 1s will cancel out quite a bit, the pi's will cancel out quite a bit, etc. But all this, it is very easy to show that this will reduce to nothing but the integral 0 to alpha sin beta 1 cos beta 1 d beta 1, very simple, you can do that in yourself, and if I perform the integration and put in the limits, this will reduce to sin squared alpha. All right. So, this is an example of the calculation of shape factor between a small area A1 and a parallel disc A2. It is a very simple example just to illustrate how to pick an area dA2 and to do the integral. Now, let us go on to another situation. I would like to calculate the shape factor using the graphs which I showed you earlier. So, let us pick on another problem. We are going to do the following. I will just state the problem today. Problem is the following. We have two rectangles like these. This is one rectangle, surface 1, and this is the second rectangle, surface 2. All right. These are two rectangles f1 to 2, dimensions are given. This is 1 meter, this is 1 meter, this is 4 meters, and this is also 1 meter. So, these are two rectangles 1 and 2, they are at right angles to each other, but they do not have a common edge. Okay. We would like to get f1 to 2. Now, mind you, I cannot read this off directly from the graph which I had earlier for two rectangles with a common edge. In that case, in that situation, remember we had the common edge situation. Here we do not have a common edge, f1 to 2 are at right angles, but do not have a common edge. Suppose I call this area, this rectangle as surface 3, and I call 1 and 3 together, 1 plus 3 together as 4. All right. Now, what can I read from the graphs which I showed you earlier? We can from those graphs get f3 to 2, this is known, or f2 to 3. Similarly, we can get f4 to 2 or f2 to 4, right. These are available to us. So, I need to express f1 to 2 in terms of these quantities, and that is what we can do very easily. We can say f1 to 2 is equal to a2 by a1 f2 to 1, here is my reciprocal relation, which from the additive relation is nothing but a2 by a1 f2 to 4 minus f2 to 3. So, I use first the reciprocal relation, then the additive relation, and when I do that, I have expressed f2 to f1 to 2 in terms of f2 to 4 and f2 to 3, which I can now read off from the graphs which have calculations which have been done earlier, which I showed to you. So, from that read off these two values for this case. I am telling you what, if you read them off, you will get the first one to be 0.34, the second one will come out to be 0.27, all right, and a2 by a1 is obviously 1 in this case. So, you will get f1 to 2 is equal to 0.07. I want you to do this yourself. That means, for both these cases, for f2 to 4 and f2 to 3, calculate L1 by W and L2 by W, then go to those graphs, read off the values of the two shape factors f2 to 4 and f2 to 3, and then you will get f1 to 2 equal to 0.07. So, I am leaving that last part for you to do to illustrate. The whole idea is to illustrate how those graphs can be used for calculating shape factors for other situations not corresponding exactly to the situation of those graphs. Now, we will stop here today.